Hi, everyone. Thank you for joining me virtually today as I talk to you about my dissertation research. I am a PhD candidate at Stony Brook University in New York, and I'm going to be talking to you about my work, Competition and Climate Change, Understanding the Future of Puerto Rican Anoles. So one thing I do want to say as we get going is that this is an active dissertation work, and because of COVID-19, my field season was canceled. And so I unfortunately do not have results for you today, but I'm hoping you'll still enjoy my talk as I talk to you about what I'm doing for my dissertation. So again, my name is Anna. I'm a PhD candidate in my third year at Stony Brook University, and I love lizards. I love lizards more than anything else I can name in this world, and I have for a very long time. And so my long-term career goals really center on doing whatever I can to improve lizard and reptile in general. I'm a fan of all reptiles, but lizard specifically conservation efforts. Thankfully, a lot of these efforts can also be useful for other reptiles, not just lizards. So moving right along. So Caribbean reptiles, right? So I realize as this is the Australian Herpetological Society, maybe I should just give a brief overview of what we have here, more on my end of the globe. So Caribbean reptiles, in the Caribbean, we have the Greater and the Lesser Antilles. And so you cannot see my mouse, but the four larger islands, so that's Cuba, Jamaica, Hispaniola, which is the Dominican Republic and Haiti, and Puerto Rico make up the Greater Antilles. That counts for 265 reptile species in total, while the Lesser Antilles, which are all of those smaller islands on the right side of the screen, make up 85 reptile species in total, for a total of 350 species of reptile in the Caribbean, which is huge. And the thing that I think is, often not thought about is the Caribbean has some really unique risks for these reptiles with respect to climate change. And so namely one is that when we think of climate change, we think of how a lot of species are going to shift their ranges, shift their distributional range. Now, because Caribbean reptiles are confined to these islands, sometimes very small islands, these range shifts become limited by the confines of a given island. And so that's one big limitation. But not only are they restricted to these islands are often impacted by hurricanes. And as climate change continues, the frequency and intensity of Caribbean hurricanes is going to change. And so I'll talk about that aspect of my work later, but what I want you to understand is that Caribbean reptiles are uniquely disadvantaged when it comes to climate change. And so my research really focuses on trying to understand how climate change and hurricanes may impact these reptiles in the long term. So anoles specifically, you guys do not have anoles unless I guess they're invasive, which I hope you don't have them because then they'd be invasive in Australia, or for all of those listening. So this is their distribution, right? So there's about 400 species of anole. They are the most species-rich vertebrate terrestrial genera in the world. So fun fact, and their distribution is everywhere from the southeastern United States, Mexico, Central America, the Caribbean, and the northern half of South America. So it's a pretty broad distribution to say the least. And these are not all Puerto Rican species because, as I meant, actually, I don't know if I mentioned that, but I work on Puerto Rican species specifically. But these are some examples of just how cool looking, I guess, anoles can be. And so the one with the very long nose, that's the Pinocchio anole found in Ecuador. You have a blue anole that's found off the coast of Colombia. The anole with the bright pink dewlap under its chin, so that thing under their chin is called a dewlap, is a very, very common anole called the green anole. It's also frequently invasive. And then there's about 400 species, more or less, depending on how you define the term species. And so they're very diverse, they're very broadly distributed, and they're often prey and predator species in all of the ecosystems in which they inhabit, making their conservation important from both an ecosystem and a species perspective. So to me, you can't really talk about anoles without talking about the ecomorph concept. Now, the ecomorph concept is not exclusive to anoles, but anoles are almost exclusively talked about with respect to the ecomorph. And so the ecomorph concept is when species have similar structural habitat usage, similar behavior, and nearly identical structural morphology, their physical appearance. And so these are the six, classic ecomorphs. For anoles, the crown giant, which is typically very large, often bright green, and inhabits the high reaches of the canopy. The trunk crown, often green as well, kind of inhabits lower reaches of the canopy. The twig anole, which typically likes to be on the ends of twigs, often found very high up in the canopy as well. Very difficult to find because it does look like a twig. Trunk anoles, which as you can imagine occupy the trunk ground, and grass bush anoles. I don't know if you can see the little thing at the bottom, but there it is, grass bush anoles. And so these are the six ecomorphs. And I think that it's really important to highlight those as I go into this talk. And so with respect to Puerto Rican anole specifically, there are 10 species of Puerto Rican anole. And all of them, or nearly all of them, there's one that's technically, if you Google it with the IUCN, it has a listing, but they're almost all unevaluated, or they are listed as data deficient by the IUCN. And this is because for most studies focusing on anoles, the studies are usually done through an evolutionary lens. Despite how much work has been done on anoles, we are really lacking ecological data. And that's just not for Puerto Rican anoles, that's for anoles broadly. That said, there are about 150 anoles in the Caribbean alone, and they are some of the more studied species of the 400 anoles found worldwide. So again, sorry about that little sidetrack there, but of the 10 Puerto Rican anole species, 5 of the 6 ecomorphs are represented. So Puerto Rico does not actually have the trunk ecomorph, that can happen on some islands. It doesn't happen on all islands. One thing I should also stress is that this ecomorph concept for anoles is only applied to the Greater Antilles, which again are those 4 islands of Jamaica, Hispaniola, Cuba, and Puerto Rico. And so the Lesser Antilles, we don't necessarily see these patterns of these 6 ecomorphs. But again, the 10 species in Puerto Rico, we do have 5 of the 6 classic ecomorphs. So I'm just going to go over the 10 Puerto Rican species that I'm working with quickly, just because this is a herpetology talk, and I think that you guys might want to see some pictures of lizards. And if you don't, close your eyes for a second. But anyway, so as I said, Puerto Rico has 5 of the 6 classic ecomorphs. They have 3 of the grass bush anoles, so that's Anoles krugi, Anoles poncensis, and Anoles pulchalis. Now, the cool thing with these guys is their tails are like 2/3 of their whole length. And so they have these super, super slender tails. And that's because they like to hang out on grasses. Most of them are, so I shouldn't say most, 2 of the 3 are pretty widely distributed. Anoles poncensis here has a more restricted range. And that's pretty much only the case with one other species that I'll talk about in a bit. The trunk crown anoles occupy the trunk up to the crowns of the trees. We have Anoles evermanni and Anoles stratulus, also have very broad distributions, and they're pretty abundant. They're pretty easy to find, pretty easy to catch. Honestly, really love working with these guys. So then we have Puerto Rico's trunk ground anoles, for which there are 3 species, Anoles chrysotellus, Anoles cooki, and Anoles gundlaki. Now, I think one thing that I like to note here, so obviously Anoles chrysotellus has an incredibly broad distribution. You could probably consider it a generalist by most respects. Anoles cooki, on the other hand, has an incredibly restricted distribution. It is the most restricted distribution of all 10 of the Puerto Rican anole species. Anoles cooki lives exclusively in the Guanica dry forest, and well, I shouldn't say that. It lives a little bit outside of it, but it really likes dry forest, and that's where the only habitat of dry forest in Puerto Rico is that southwest corner that you see on the map there. So lastly, we have the crown giant and the twig anole. So the crown giant here is Anoles cuvieri. They're often very large, found very high up in the canopy. It's the only Puerto Rican anole that if it bites you, you'll probably bleed. Very opposite of the twig anole, Anoles occultus. It's a very cryptic species, very difficult to find, and it's tiny, tiny. So if it bites you, you're probably gonna laugh at it. You're probably not gonna have any blood drawn, and you're just gonna kind of say, oh, that's sad. I'm sorry that when you bite me, it doesn't hurt at all. And so those are the 10 species of Puerto Rico's anolis lizards. varying in their distribution to some extent, varying in their size, but all falling into one of those 6 classic ecomorphs. So now I'm going to jump into a bit of what I do with species distribution models. Now, I know this talk has people who are experts in the field, as well as people that are just interested in herpetology in general. And so I really don't want to dive into all the specifics of the modeling that I do. I want to make this talk as accessible as possible. So just quickly, as a brief explanation of what these models do, species distribution models use occurrence records and environmental variable layers, that environmental data, and they put all of those data into some algorithm. There's a variety of algorithms you can use. And ultimately, you get this output of this habitat suitability map that's sometimes called a prediction map. And so this occurrence data, when we think of occurrence data, think of, okay, we go into the field, we see one individual, we record the coordinates, the latitude and longitude of that single individual. That is a single occurrence record. So we have hundreds and hundreds of these records. And then we have environmental data. And what those could be climatic variables like precipitation, temperature. They can also be things like, slope of a mountain. They could be soil chemistry, soil pH. Pretty much anything under the sun can be an environment. I shouldn't say that, but there are plenty of different environmental variables that can be created as these environmental variable layers. And what this algorithm does is it says, okay, we have occurrence records at all of these, coordinates, and all of the environmental variable layers are also like in a coordinate system. And so what the algorithm can do is it can say, okay, this species is only found at coordinates that correspond to this range of this environmental variables values. So in this range of precipitation values, in this range of temperature values, that means that species must have that must be what it finds suitable for that specific environmental variable. So it can kind of the algorithm can make those connections, it can make those correlations, and it can say, based on these data, this is what we predict is the species' suitable habitat. And then what you can do further with climate change or with land use change is you can say, this is how we expect these environmental variable layers to change in the future. So based on that, how do we predict the suitable habitat range of that species to change in the future? That's going to be my brief overview of species distribution models. If you have questions, please do not hesitate to contact me or ask me after this talk. Another thing I would like to say is that species distribution models are also commonly called ecological niche models. And I say that because understanding what a niche is very, very important with respect to understanding how species distribution models work and why I'm trying to do what I'm trying to do for my dissertation. So when we think of a niche, we often think of this BAM diagram. It's called the BAM diagram. And the B stands for biotic, the A stands for abiotic, and the M stands for movement. The idea is that inner triangle where there's an arrow pointing that says occupied distributional area, that is the species' realized niche. And I'll go over in a second the difference between the realized niche and the fundamental niche. But what you have to understand about this niche here, this little triangle in the center, is that is where the species is living based on, it's biotically suitable. So that means that there aren't so many predators that the species can't be there. There aren't competitors out competing it. It's biotically able to be there. Abiotically means that, based on all these environmental variables, so precipitation, temperature, soil chemistry, like slope, whatever it might be, all of these abiotic factors are such that these species can live there. It's abiotically suitable. And then lastly is movement. And movement, I think, is an easy one to overlook, but it's incredibly important because if the species can't get somewhere that is biotically and abiotically suitable, then it cannot be its niche. And so the example I like to use with this is if we're thinking of, you have a little island in the middle of a lake or something, and maybe that island is abiotically and biotically suitable for some mammal species. However, this mammal species cannot go in water. Okay, that means that even though that island is abiotically and biotically suitable for that species, it cannot represent that species' realized niche because that species cannot physically get to that island. So these three factors come together to make the species' realized niche. And the reason I stress that is because with respect to species distribution models, most species distribution models model the fundamental niche, even though what we really need to be modeling is the realized niche. Now, the fundamental niche represents all of the areas that the species could theoretically occupy if it could get there. Okay, if it could get there, and if it didn't have, predators or competitors that again were eating it or competing with it. Right? And it had the prey available to it that it needed. So the fundamental niche represents all of the areas it could theoretically occupy. But the realized niche represents this n-dimensional hypervolume, this space that is actually what the species occupies. Okay? So just because a species can occupy the entire island of Puerto Rico doesn't mean that it does occupy the entire island of Puerto Rico. And so, a very interesting thing that people try to address with species distribution models is what brings the model from modeling the fundamental niche everywhere it can occupy to actually modeling where we find the species, the realized niche. And a big part of that, we all believe in the distribution modeling community, is a big part of that is probably due to these biotic interactions like competition, predation, mutualistic relationships, things like that. And again, the reason I like to stress in the beginning, the ecomorph concept, now that I've explained that to you, I can very adamantly tell you that is not equivalent to a niche. And also, maybe you guys say niche in Australia. We say both here. To us, neither one is wrong or right. I say niche. I'm sorry if you prefer I was saying niche. But anyway, the niche or niche is not equivalent to the ecomorph concept. And I like to use this example with the trunk ground anoles in Puerto Rico because, right, so they're all the trunk ground ecomorph. But the ecomorph concept does not have anything to do with climatic preference, which is an incredibly important dimension when we're thinking about a species' niche. And you can see that here because if we look at the Cook's anole, Anolis cooki, that middle species' distribution in the southwest corner of Puerto Rico, that species has the same structural habitat preference, trunks of trees in the ground, the same physical morphology. And if you look at these three species, you can probably see that. And very similar behavior to the other two species, but yet their distributions are very different. And it's because, at least when you're comparing, say, Anolis cristallis, which is the crested anole, or Anolis cooki, which is the Cook's anole, Anolis cristallis can occupy pretty much any climatic habitat under the sun with respect to Puerto Rico, but Anolis cooki can only inhabit dry forest, which is only found in the southwestern corner of Puerto Rico. And so those dimensions of the niche are not represented in the ecomorph concept. And I just like to stress that because I think they're so commonly interchanged in conversation, and it's just wrong. And so I'd like to stress that just before I get into what I'm actually doing with these SDMs and the limitations of SDMs. So again, I just said limitations of SDMs, but so biotic interactions are a big limitation, as I've just discussed. So things like we're not incorporating competition, we're not incorporating predation. What does that mean for these models? And then extreme weather events like hurricanes and droughts, which I'm going to talk about less so in this presentation because it's a very quantitative part of my dissertation. It's one that I find very interesting, but I don't want to weigh you down with all the mathematical modeling that we're doing here. So I'm going to dive right into the limitations of biotic interactions. And I pretty much just stressed to you why it's so important to incorporate these interactions. So a species might be able to be found in a given region. Theoretically, its fundamental niche might say it would be found there, but maybe it has competitors there that would outcompete it. Maybe there are predators there that would consume it. Maybe it can't be there for some reason that has to do with the biotic interactions it would have. Now, this is really important when we're trying to think about climate change, because climate change is, projected to shift species distributions as species try to track that shifting climate envelope. Now, because of this, there's probably going to be some amount of novel interactions forming and past interactions changing, maybe even interaction strengths changing due to climate change. And so trying to understand how biotic interactions, if we incorporate them into these models, how they might change the predictive power of the models I always have thought is very important for trying to understand how climate change might, change distributions. And so what I'm doing to try to get at this question is I'm conducting these manipulation experiments, these removal and addition experiments on Puerto Rican anoles to try to quantify the strength between different pairs of species. And then I'm actually going to incorporate that competitor strength into these models. So I made up this little, I don't know if you'd call it a schematic, to illustrate the theory behind these removal and addition experiments. So say we have two species here, species A and species B. In this first slide, you see that both species are in their equilibrium population sizes. Now, that doesn't mean that they're the same population size, but it means that their population sizes are such that they can mutually coexist, right? Now, say we remove a bunch of individuals of species B, say like 50, 60%. How will species A respond, right? So what I'm doing is I'm removing individuals of species B, whatever that species may be, given the plot that I'm using and the treatment that I'm using, and looking at how the other species, in this case, species A, will respond. Now, in one angle, it's expected that species A will now have access to more resources because so many individuals of species B have been removed, and we will see that species A increases in abundance following the removal of species B. Now, although we will hopefully see in this, we're hoping as in our hypothesis is true, this increase in abundance, that increase in abundance could also be a migratory effect, right? So you take away a bunch of species, a bunch of resources become available, maybe you take away a bunch of individuals, a bunch of resources become available. You could maybe see that there be individuals in other areas of the forest that, take notice and they migrate to that area where the individuals were removed, because these plots are open plot design. We are doing open plot design because we want to see if there's any population level changes that take place. Now, to try to get at this issue of dispersal, what we are doing is we are also measuring every single individual's body mass, I should say every single individual that we capture, its body mass, if it is pregnant, and its stage. So we're going to be seeing, when there's more resources available, does species A not only increase in abundance, but does individuals of species A exhibit an increase in body mass, an increase in the number of pregnant females, or an increase in the number of offspring or juveniles, all of which are indicative of more resource allocation to species A, and therefore indicative to competition technically taking place between species A and species B. Now, on the reverse, yet somewhat in parallel, we go back to these two species at their equilibrium population sizes, but this time we add individuals of species B. Now, what's going to happen to species A? So it is likely that species A will then, we will see a decrease in the abundance of species A because there will now be fewer resources available to species A. So it's just, the other side of a coin here. So now that species A has less resources available to it, we expect to see a decreased abundance of species A, but also a decreased number of pregnant females, a decreased body mass, and a decrease in the number of juveniles or offspring. Or I keep saying offspring, but I mean newborns. And so going off of that, we can, with all of this data, we can quantify the competitor strength between these species. And so what I've done, so I'm only, even though there are 10 species of Puerto Rican anole, I am using 3 species such that I can look at the difference between if they are the same ecomorph or different ecomorph. So the 3 species I'm using here are Anoles chrysotellus, Anoles gundlachii, and Anoles evermanni. Anoles chrysotellus and Anoles gundlachii are both trunk ground anoles, while Anoles evermanni is a trunk crown anole. So you can hear, even in just the name of the ecomorph, they both occupy the trunk, but gundlachii and chrysotellus go onto the ground, while evermanni goes up into the crown, the canopy of the tree. And so I'm doing different combinations of these species to see, which comes out on top, which is the greater competitor with respect to different combinations. And so this is just a general experimental setup. This is not representative of the actual layout of the plots, but pretty much you can see here, removal of species 1, we have 2 treatments, we have 2 replicates of that, and then we systematically add a certain number of species species 1. And the reason we're also doing addition is because it was truly just a conversation of, well, if you're capturing so many to remove, what are you going to do with them? And it came down to, let's just add them to other plots in a systematic way and see if we kind of get like a paralleled response. And so that's what we're doing. So we have these 2 treatments, removal or addition, and we have it with 3 different species in different combinations, and then we have our 6 controls. And so all of this field work was supposed to happen last summer, but because of COVID-19, it was canceled. So the plan is to tentatively have it during the 2021 summer. And then this is just the spatial layout of the plots. And so C are the controls here, C1, C2 through C6 are the controls. The removals are 1 through R6, and the additions A1 through A6. And the nice thing about this, when I say the nice thing, one of the nice things about this project is this land, which is located in Angeles, Utuado, Puerto Rico, is owned privately by a University of Puerto Rico professor, Dr. Alberto Puente Rolón, and he's also my external committee member for my dissertation work. And he has just been such a gem with respect to helping me with everything. And so this land is owned by him and his wife, and she is also a professor at a different University of Puerto Rico campus, and they both work on Puerto Rican anoles. And so this is on their property, and this is where I will also have about 10 to 12 University of Puerto Rico undergraduate biology students acting as my field assistants, and they'll help me in the field as we collect all of this data. And we'll be collecting it using mark recapture methods. And so we use VI alpha tags, and VI alpha tags allow for the individual identification of whatever species you're working on. And so you can see the little tags on the legs here. And so it's actually like a letter and then a sequence of numbers. And there's also different colors you can get. And this method is just, there are other methods you can use for tagging these individuals. You could use toe clipping. I personally don't like toe clipping. And the issue that I've seen with toe clipping is that if the toe is clipped and becomes infected, then that individual becomes at a heightened risk of predation, which would skew the results of the study. Similarly, there's other methods like you sew beads onto the back of their necks, or you can, color them with Sharpie. However, sometimes those actually make them more at a heightened risk of predation as well, because it's so visible to predators. These tags are very difficult to see. We insert them between the subcutaneous layer and the muscle layer of the skin. So it's actually through this top translucent layer of skin. So you can see the tag through their skin, and it doesn't fall out. It pretty much stays with them until they die. And the only thing is you really do need to typically capture them to actually read the tag, but they're incredibly useful. So we'll be using these mark recapture methods. And the other thing with these mark recapture methods that's so powerful is because we're individually identifying anoles, we can calculate some of these demographic parameters that don't have data, that data doesn't exist for right now. So like growth rate, population size, mortality rate, different metrics like that that are needed by the International Union for the Conservation of Nature when it comes to actually, looking at a species' risk of extinction and risk of decline. And so again, a lot of the studies on anoles are done from this evolutionary perspective. And so although there have been so many studies on anoles, we're really lacking in ecological data. But thankfully, I'll be able to get a lot of that data, at the very least for 3 species, but hopefully more throughout the course of my field work. So I kind of went on a tangent there about my survey methods, but ultimately we're going to have all this data on competition. So what can we do with these data? So the idea is we're going to be able to quantify competitor strength for different pairs of anole species. And then I am going to create a competition rule to be used in stacked species distribution models. I don't want to go into what those are just for the sake of time and for the sake of avoiding really heavy quantitative methods, but pretty much it's for instead of just individualistic species distribution models, you're predicting species richness. So the number of species found in a given region or grid cell. And so I'm going to make this competition rule with that field collected competition data in order to constrain the species richness predictions for Puerto Rico. and then under different climate scenarios. And so that's pretty much what that last point says there, with integrating experimental competition data into the distribution models to see if that integration of competition data improves the predictive power of these models. And so the idea, if I can make this work, is that that will be useful for, you know, understanding how anoles might be affected under climate change, but also these methods are incredibly transferable for numerous species. And so I'm hoping that these methods will prove useful or provide valuable insight into the models. What I think is actually kind of exciting about them is, so obviously you always want to, people always say, journals always say you should have a significant result. That said, the significant result here would probably be along the lines of, oh yes, you have to incorporating data, experimental data on biotic interactions improves the predictive performance of the models. So that's great if it does, but what it means is that all of these studies that have used proxies for competition or proxies for biotic interactions in the models, it pretty much means that's not good enough. And that's almost unfortunate, because using proxies is easier than collecting all the field data that I have to collect to test what I'm testing. So in some ways, to me, if I find that it doesn't improve the predictive power of the models, I kind of think that's a good thing in some ways too. It means that these proxies are doing a good enough job. They're getting the job done. And I think both perspectives are really useful. So, you know, stay tuned. We'll see what the outcome is in a few years. The other thing I'm doing is abundance surveys. And I'm just going to touch on these quickly, but pretty much I have 25 plus sites. They're not all represented by the little green tacks on the map above, but some of them are. 25 plus sites throughout Puerto Rico, and in order to get occurrence records on all 10 species of Puerto Rican anole. This will supplement the data that I'm getting from GBIF, the Global Biodiversity Informatics Forum, for which there are a lot of occurrence records for Puerto Rican anoles, but I would like to have my own data, as well as collecting absence data, in which case GBIF usually only has presence data, and presence absence data is a lot more useful for species distribution models. So I'm hopefully going to get some absence data on all 10 species once I can conduct these abundance surveys. And the reason this is also, you know, an interesting thing for me to have and for me to do, at least in my opinion, is that there is actually a method that allows you to quantify competitor strength between species using habitat variables as covariates, and the abundance or the population size in an area. And so what I'm hoping to do is get the abundance data and collect habitat variable data at all of these 25 sites, and then quantify competition that way, so we can try to see if competitor strength between different pairs of species changes across habitat types. Now, we hypothesize it will, but you know, how much? Maybe not for all species. How does this factor into our predictions with climate change? So there's a lot of interesting questions we can ask if we can get a better insight into those relationships. So switching gears to extreme events, extreme weather events. So in the Atlantic Basin, which includes the Caribbean, under different climate change scenarios, hurricanes are predicted to change in frequency and intensity. They are technically predicted to increase in intensity through time, but decrease in frequency. So we have more really large hurricanes and fewer hurricanes overall, but the ones that hit would be probably very impactful. And so, you know, a lot of models, what they use is they use these long-term climatic averages in their environmental variable layers for their species distribution models. The issue with this is that these types of extreme weather events, and so for me, I'm looking at hurricanes, they are very capable of partially shaping the distributions of species. And so these two figures here, one is representative of Hurricane Hugo, which hit Puerto Rico in 1989, and the other of Hurricane Maria, which hit Puerto Rico in 2017, show that these hurricanes drastically impacted the vegetative cover of the island. And, you know, when we think of anoles, we think of them in the forests, we think of them on the trees, in the canopy. And if these forests, this canopy structure is being completely destroyed by these hurricanes, then it's actually going to be really important to understand just how just how hurricanes might potentially shape the distributions of anoles, for the current distributions, but then also in the future as climate change is predicted to change the frequency and intensity of hurricanes through time. And so Caribbean hurricanes, what I'm really asking is, how are hurricanes going to impact the future distributions and long-term viability of Caribbean reptiles, specifically anoles, but again, these methods are widely transferable. And so these are just some pictures of how hurricanes have gone through the Caribbean, but also just the destruction of El Yunque National Forest here. And so hurricane data really poses the biggest limitation with respect to this work, because hurricane data is not often ecologically accessible. And what I mean by that is that hurricane data is at least at the National Hurricane Center, is at a scale, a spatial and temporal scale that is not transferable to working with ecological studies. The spatial scale is too large, the temporal scale is too long. And so what I am doing, I am collaborating with another PhD candidate at my university, Stony Brook, who is a PhD candidate in the School of Marine and Atmospheric Science. Her name is Alyssa Stansfield. I meant to throw a picture of her up in here, but it's okay. She'll forgive me. And this is actually a climate change specialist group activity through the IUCN. And we are extracting data from local Puerto Rico weather stations based on this algorithm that I'll explain to you. So pretty much in this bottom right-hand corner here, you see this, well, you can barely see it, but you see this red circle. In the center of this circle is Puerto Rico. And this red circle represents a 500-kilometer radius circle from the center of Puerto Rico. All of these blue lines are hurricane tracks over, I think, the past 25 or 30 years. And they're when the eye of the storm passes through that 500-kilometer circle. In the past 25 or 30 years, that has happened 344 times. These are hurricanes from categories 1 to 5, as well as tropical depressions and tropical storms, which are technically at a lesser degree of intensity than the hurricanes at categories 1 through 5. So what we are doing is say, we go to the National Hurricane Center's database, we say, if the hurricanes, the eye of the hurricane's track fell within this 500-kilometer radius circle, so that's in the National Hurricane Center, go into the weather station data sets and pull out the timestamps from each of those weather stations that corresponds to when the eye of a given hurricane was within that 500-kilometer circle. The National Hurricane Center has track data and overall hurricane wind speed, precipitation data, but it does not have this localized data. And so we're actually going into the weather stations and saying, we want the wind speed on the ground at that weather station at this exact time, and we want the precipitation at this exact time. And that data becomes ecologically relevant for us to use in these models. And so we're doing this with both species distribution models and population models in hopes of understanding how hurricanes through time may have or may in the future affect the distributions and long-term viability of these Puerto Rican lizards. So I'm really excited about this work. I'm excited to be working with the IUCN and again, Alyssa. And so we're always looking for insight on people who have done ecological studies with hurricanes. So if you know anyone or you are one of these people, I would love to talk to you. So please reach out. But anyway, this is what we are doing with the hurricane data. And I think it's going to be really exciting. I can't wait to have results in a few years about this. So I would like to thank so many more people that I can fit in the screen. But I mean, I guess I would probably primarily like to thank my lab at Stony Brook University, the Akchakaya lab, my advisor, Rashid Akchakaya, as well as, and so that's a picture of my lab on the right side of your screen. And then also I have so many wonderful collaborators in Puerto Rico, Alberto, Sandra, Eliasim, Neftali, and they have all been pivotal in just teaching me so much about the Puerto Rican Anoles, but also just helping me recruit University of Puerto Rico undergraduate students and just learning the lay of the land with the island. And also, I guess, my manipulation experiments are on Alberto and Sandra's land, their private land. And so I couldn't be more thankful. And also, I would like to give a special thank you to the Maldonado Ecology family, who graciously hosted me when I was in Puerto Rico during the 2019 summer, March 2020 before COVID hit, and ideally next summer and beyond. And so they make my life so much more wonderful than it already would be there. So so many people to thank and so many more. And thanking you, of course, for listening to my talk. I hope you enjoyed it. Please, if you're interested, check out my website or my Twitter. My research Instagram is a bit dead right now because I have no new field photos because COVID took that away from me. But I would love to hear from all of you, and I really hope you enjoyed my talk. And I just thank you so much for this wonderful opportunity. Thank you.